Imagine what would happen if we had a uniformly loaded frame, where one of its legs is fixed and another is supported by a roller. In previous video, we already know what kinds of frames are prone to sidesway. The frame under this condition is not symmetrical, where one support restrains everything and another allows lateral movement. Therefore, we should expect the vertical members are having different internal moment, and this causes frame to sidesway. Bear in mind that we always consider internal moment that acts in clockwise direction as positive moment. By segmentizing the frame members, we have found something interesting. For member A, B, and B, C, slope deflection equation applicable for internal span and end span with far end fixed is implemented. For member CD, internal moment at both ends should be 0. At node D, no moment can be carried by roller support. At node C, the member will not be in equilibrium if moment is developed here, since there is no lateral reaction force at node D that can counteract it. To simplify the equations, we calculate FEM for internal moment MBA and MBC. Other FEM terms should be eliminated since they are non-existent. We already know that this frame is prone to sidesway. Therefore, we need to assume both node B and C are displaced by magnitude of delta towards the same direction, assuming the frame is swaying towards the right hand side. This causes the vertical member AB to rotate in clockwise direction, and therefore, the sign of delta should remain positive. For horizontal member BC, the term delta is eliminated since it is not the one involved in sidesway. By checking the boundary conditions of members, we can conclude that only point A does not allow rotation. Therefore, we proceed with eliminating theta A and remain both theta B and theta C in the equations. We are good to simplify the equation again at this point. Our slope deflection equations consist of 3 unknowns, namely theta B, theta C, and delta. We can construct 2 out of 3 required equations by taking moment equilibrium at node B and C. The third equation is built by taking equilibrium in global horizontal direction. For node A, the horizontal reaction force equals to shear force in node A of member AB. In other words, by solving this shear force, we can solve for the reaction force, recalling that roller at node B does not provide horizontal reaction. Therefore, the equilibrium equation is simply AX equals to 0. With these simultaneous equations, we can start to solve for the unknowns. In this example, we choose to use matrices to solve them. With the aid of Microsoft Excel, the answer can be obtained easily. As usual, we substitute the parameters obtained from simultaneous equations and determine the internal moments. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.